Welcome to the Explainer. Today, we're going to completely demystify something absolutely fascinating: how computers actually see and interpret the visual world around us. We take our own human vision for granted, right? But for a machine, a photograph isn't a beautiful landscape or a recognizable face. It's just a massive, flat grid of numbers. Well, today, we're bridging that gap. Just imagine for a second how a self-driving car navigates a super busy city street. Think about it. How does it look at this chaotic, endless stream of data and instantly recognize, say, a road boundary, a stop sign, or a pedestrian stepping off the curb? I mean, it's a monumental task. The machine literally has to find order in all that visual noise, and it pulls this off through a series of absolutely brilliant, pixel-level mathematical translations. So the absolute foundational step in making sense of all this data is a process called image segmentation. Think of it kind of like taking a highly detailed, super realistic photograph and turning it into a simple coloring book. The computer analyzes the image and groups identical, or at least very similar, pixels together into discrete, manageable segments. So instead of dealing with millions of individual, overwhelming points of light, the machine can now simply say, okay, this cluster of pixels right here is a car, and this cluster over here, that's the sky. It's a real game changer. Okay, here is our macro to micro journey for today. First, we'll look at real-world uses. Second, detecting lines. Third, the fundamentals of edges. And finally, number 4, the Canny edge detector. All right, section 1, real-world uses. Let's explore exactly why segmentation matters so much. These applications touch literally almost every aspect of our future. In medical imaging, for example, segmentation is the exact thing that allows software to scan an MRI and instantly highlight an anomaly or a tumor, which helps doctors diagnose patients way faster and far more accurately. And for self-driving cars, which, remember, are processing millions of pixels per second in real time, it's the literal difference between staying safely in a lane or veering right off the road. It also enables robots to know exactly where an object begins and ends so they can actually grab it. It allows satellites to map out urban sprawl. And hey, on a lighter note, it's the exact same tech that lets you instantly cut out the background from a photo on your phone. Pretty cool, right? This is exactly why mastering this technology is absolutely crucial. Moving right along to section 2, detecting lines. This is all about finding the geometry. So, one of the dominant techniques for doing this is called the Hoff transform. Now, I know that sounds a little intimidating, but in plain English, it's really just a mathematical tool used to find points that form a straight line, even when the image is super noisy or parts of the line are totally hidden. It essentially takes points on an image and maps them into an entirely different mathematical space where finding straight, continuous lines just becomes a matter of simple geometry. Now, take a look at these grids of numbers. These are called detection kernels. Think of a kernel as a tiny little mathematical stencil that the computer slides pixel by tiny pixel over the entire image. If you look at the numbers inside them, by arranging positive and negative numbers in very specific patterns, like horizontal rows, vertical columns, or diagonal slants, the computer can actually calculate whether the pixels underneath that stencil form a line pointing in that exact direction. It's so clever. And this brilliantly illustrates the result of using one of those stencils. When you start with an original image, like a wire bond template that has lines going in literally every possible direction, and then the computer slides a plus 45-degree detector kernel over it, the result is practically magic. It effectively strips away all the visual noise. All the vertical lines, gone. Horizontal lines, gone. It leaves behind only the diagonal lines that perfectly match that exact 45-degree angle. It's a highly, highly targeted search. Okay, section 3, the fundamentals of edges. Let's talk about locating the boundaries. An edge, at least in the eyes of a computer, is defined simply as a sudden, sharp change in brightness. It is an abrupt transition. Imagine you're walking down a bright, sunlit, white concrete sidewalk, and then you step immediately onto dark, black asphalt. That stark contrast right there, that sudden drop in intensity, that is exactly what the algorithm is hunting for, to figure out where one object stops and another entirely different one begins. If you trace your eye across the different models here, you'll see exactly how a computer mathematically represents these different types of edges. On one hand, you have a step edge, which basically looks like a sheer cliff face on a graph. Then you have a ramp edge, which is a much more gradual slope, representing a softer, blurrier transition. And finally, there's a roof edge. This one spikes straight up and immediately drops back down, kind of like a thin sliver of light in an otherwise completely dark room. To contrast these a bit further, a step edge represents an ideal, instantaneous change. Honestly, it's the perfect razor-sharp boundary we'd all absolutely love to find in our data. But as we know, the real world is messy and often pretty blurry. A roof edge, on the flip side, represents a different kind of feature entirely. It's an intensity that peaks and then immediately ramps right back down. This usually indicates a thin line or maybe a ridge in the image, rather than the hard boundary of a large object. Now, to actually find these abrupt changes, computers have to lean on calculus. They compute what's known as the first derivative. But hey, don't worry about the complex math here. Just know that the first derivative simply measures the rate of change in pixel intensity. So wherever that rate of change is the absolute fastest, meaning it has the highest gradient value, the computer flags it and goes, aha, there is a sharp edge right here. Algorithms like the Sobel operator or the Laplacian of Gaussian, those are the famous heavy-hitting tools built specifically to calculate these exact steep gradients. Which brings us to Section 4, the Canny edge detector. This is truly the gold standard algorithm. So the absolutely crucial point of the Canny algorithm is its incredibly strict dual objective. First off, it demands a low error rate. That means it must not miss any real, true edges, and it definitely shouldn't get fooled by random static or visual noise. Second, the edge points it does find, they must be perfectly localized. It's just not good enough to say the edge is around here somewhere. No way. The algorithm has to pinpoint its exact location with extreme, pixel-perfect accuracy. To achieve this level of perfection, the algorithm walks through a super elegant multi-step process. Step 1, it actually blurs the image just a little bit using a Gaussian filter. This is basically like squinting your eyes so you can ignore the tiny, irrelevant static and just focus on the big shapes. Next up, it computes the gradients, finding those super steep brightness changes we were just talking about. And finally, it applies something called non-maxima suppression. Now, that is a very fancy term. But honestly, all it really does is thin out the thick, blurry edge lines until they become razor-sharp boundaries that are exactly one single pixel wide. The final magic trick of the whole Canny algorithm is connecting the dots. Because, even after all that heavy processing, sometimes an edge might still have a tiny little gap in it. The algorithm fixes this by evaluating weak pixels and strong pixels. It meticulously traces along the line, and if it finds a weak edge pixel that happens to be directly connected to a strong, confirmed edge pixel, it promotes it. It links them together, bridging the gaps to create a flawless, continuous, totally unbroken boundary right around the object. By transforming the physical world into a grid of pixels, and then turning those pixels into perfectly segmented lines and edges, we are quite literally giving machines the gift of sight. So I want to leave you with this to really think about. As these microscopic, highly complex mathematical calculations become even more instantaneous and completely pixel perfect, what entirely new transformative capabilities is this going to unlock for artificial intelligence in our daily lives? Well, thank you so much for joining me on this explainer today, and remember to keep looking closely at the world around you.